Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 27, 2025, about 3 days ago. This paper introduces multiplayer Nash preference optimization, which generalizes Nash learning from human feedback to many players and, notably, scores 57.27% on Alpaca Eval 2.0, 52.26% on Arena Hard, and 7.03 out of 10 on MT Bench, surpassing prior baselines. The paper is titled Multiplayer Nash Preference Optimization, and the implications for model training are quite significant. In short, it frames alignment as an n-player game with reference regularization, defines multiplayer Nash equilibria and a duality gap, and shows stronger robustness under heterogeneous annotators. Also, the authors shared a GitHub repo. It packages the full MNPO training pipeline with MNPO scripts for orchestration, on-policy data gen for preference pairs, alignment utilities, YAML training and accelerate configs, plus a run.sh that ties it all together. You'll find environment setup, multi-GPU training, VLLM serving, and eval scope evaluation examples. So, Table 1 conveys that time-dependent MNPO serves as a unifying umbrella that reproduces many preference optimization algorithms under specific settings. The table lists how the number of players, the chosen opponents, and the importance weights map to each method. Importance weights mean how strongly past policies influence the opponent mix. The distance term uses either squared distance or a backward Bernoulli KL divergence, which is a way to measure differences between probabilities. Alright, Table 3 compares models on instruction, knowledge, and common sense tasks, and reports an overall average, so it summarizes broad capability rather than a single skill. The average shows MNPO on top at 71.08. Instruction strength remains competitive, with IF eval around 73.94. Knowledge includes hard exams like GPQA, where scores are lower, yet MNPO still ties or edges others. The pattern suggests that multiplayer training yields balanced gains across categories. So, Table 2 ranks instruction following performance across methods, which tells us whether multiplayer training actually wins head-to-head. An automated judge model, GPT-5 Mini, scores responses, meaning a model acts as a consistent referee. MNPO reaches about 57% on Alpaca Eval 2.0. The score is about 52% on Arena Hard. The result is about 7.0 on MT Bench, which edges two player baselines of similar size. Moving from instruction results, Table 4 reports math and coding performance, which reflects reasoning depth and code synthesis skill. This table highlights competitive scores across GSM 8K and Minerva Math, while AIME 24 is a tougher short answer exam where most baselines hit 0. The bottom row shows MNPO reaching 61.59 on human eval and a small but non-zero AIME 24 result. The rightmost average column lists 48.10, so the multiplayer method leads this set. Alright, Table 5 organizes the landscape of preference optimization methods, showing how each objective fits into a common template that balances winning rate against a reference policy. The table lists whether a reference policy is used, whether the current policy appears explicitly, and whether training is offline or online. This catalog matters because it reveals shared structure across DPO, RLHF, IPO, ORPO, and the Nash variants, which MNPO generalizes. The objectives differ mainly in the divergence, or loss form, and in how comparisons are aggregated. Alright, two takeaways stand out. Multiplayer Nash preference optimization treats alignment as an n-player game with a clear duality gap target, and the approach consistently beats two-player baselines across instruction, reasoning, and coding. The broader implication is practical robustness to diverse, non-transitive human preferences. Thanks for listening. I am Alex.